sklearnneighborskneighborsgraph. Description: this function constructs the k-neighbors graph for a given dataset. The graph is represented as a sparse adjacency matrix, where non-zero entries indicate the presence of an edge between two data points. An edge exists between two data points if they are among each other's k-nearest neighbors. This function utilizes various distance metrics to determine the nearest neighbors, allowing for flexible graph construction based on the dataset's characteristics. Inputs: X. This input represents the dataset for which the k-neighbors graph is to be constructed. It is a 2D array of shape n samples, n features, where each row represents a data point and each column represents a feature. N neighbors. This parameter determines the number of nearest neighbors to consider for each data point. It directly influences the sparsity of the resulting graph. A higher value of n neighbors leads to a denser graph with more connections between data points. Mode: this parameter specifies the type of graph representation. It can take the values connectivity or distance. If set to connectivity, the adjacency matrix will contain only ones and zeros, indicating the presence or absence of an edge. If set to distance, the adjacency matrix will contain the actual distances between neighbors. Metric: this parameter defines the distance metric used to calculate the distances between data points. It can be a string specifying a supported metric, e.g., Euclidean, Manhattan, cosine, or a user-defined callable function. Includes ELF. This Boolean parameter determines whether to include self-connections in the graph. If set to true, each data point will be considered its own nearest neighbor. Njobs: this parameter controls the number of parallel jobs to run for computations. It allows for parallelization to speed up the process, especially for large datasets. Outputs: this output is a sparse adjacency matrix representing the constructed k-neighbors graph. Its shape is n samples. N samples, where each row and column corresponds to a data point. Non-zero entries in the matrix indicate the presence of an edge between two data points. Steps: for each data point in the input dataset X, the algorithm finds its k-nearest neighbors based on the specified distance metric. The algorithm constructs a sparse adjacency matrix A, where each entry ai, j represents the connection between data points I and j. If mode is set to connectivity, the entry ai, j is set to 1 if data point j is among the k-nearest neighbors of data point I, and 0 otherwise. If mode is set to distance, the entry ai, j is set to the distance between data points I and j if j is among the k-nearest neighbors of I, and 0 otherwise. Metrics: distance metric. The choice of distance metric significantly influences the resulting graph. Structure: different metrics emphasize different aspects of the data, leading to varying graph connectivity and neighborhood relationships. Visualization plots. Graph visualization. The constructed k-neighbors graph can be visualized using graph plotting libraries to understand the relationships and connectivity patterns within the dataset. This visualization can help identify clusters, outliers, and other structural characteristics. Fine-tune parameters. N neighbors. Adjusting the value of n neighbors directly controls the sparsity of the graph. A higher value leads to a denser graph with more connections, potentially capturing more global relationships. A lower value results in a sparser graph, highlighting more localized relationships. Metric. The choice of distance metric can significantly impact the graph structure. Experimenting with different metrics can reveal hidden relationships within the data and improve the accuracy of downstream tasks. Uncertainty methods. None, this function does not directly handle uncertainty estimation. However, by leveraging different distance metrics and analyzing the resulting graph structure, insights into the uncertainty of neighbor relationships can be obtained. For example, a higher number of neighbors or a wider range of distances between neighbors could indicate higher uncertainty in the neighborhood assignment. Challenges and fixes. Challenge 1: choosing the appropriate distance metric can be challenging, as it directly impacts the neighborhood relationships and the resulting graph structure. Sample use case that resulted in challenge 1: when dealing with data containing both continuous and categorical features, using a single distance metric might not be optimal, leading to inaccurate neighbor assignments. Fixes to challenge 1: consider using composite distance metrics that combine different metrics for different feature types. For example, using a weighted combination of Euclidean distance for continuous features and Hamming distance for categorical features. Challenge 2: the computational cost of finding nearest neighbors can be high, especially for large datasets or when using complex distance metrics. Sample use case that resulted in challenge 2: when working with a massive dataset containing millions of data points, calculating the distances between all pairs can become computationally expensive. Fixes to challenge 2: explore approximate nearest neighbor search algorithms, such as KD tree or ball tree search, which can efficiently find approximate nearest neighbors without computing all pairwise distances. Utilize efficient data structures and algorithms for distance calculations, such as specialized libraries optimized for specific distance metrics. Consider parallelizing the computations to distribute the workload across multiple cores or processors.